All right, good evening, everybody. This is topic 4.1, bonding for SL only, but if you're an HL and you want some extra practice, you may as well look at it as well. So we're going to look at ionic bonding, covalent bonding, resonance, metallic bonding, Lewis structures, and allotropes. Okay, here we go. All right, so this is stuff we should already know. Cations are formed when metals lose electrons, and when they lose electrons, that means they form positive ions. And anions are formed when nonmetals gain electrons and form negative ions. So this is the IB definition of ionic bonding. You're probably going to see this in multiple choice questions. It's electrostatic attraction between oppositely charged ions. Whenever we say electrostatic attraction, we just basically mean positive charges being attracted to negative charges. All right, so when ionic compounds are formed, there's a transfer of electrons from one element to another. So if we look here at the top, we see sodium reacting with chlorine. Now, chlorine has a very high electronegativity, which means it readily gains electrons. And sodium has a very low ionization energy, which means it's willing to give up electrons. It's really easy to remove them. So when chlorine comes in contact with sodium, it will remove that electron and become a chloride ion. In the process, it also makes sodium into a sodium ion. Now, once they become ions, they're positively and negatively charged, so they attract each other and stick together. Now, we can determine whether or not a reaction between two compounds will form an ionic or a covalent compound, and that's by looking at the electronegativity difference. So when two atoms are bonded together, we can look at their electronegativity values, get the difference between them, and the result will tell us what kind of bond we have. So if there's a zero electronegativity difference between them, then the bond type will be a nonpolar covalent bond. We'll talk a little bit more about polar, nonpolar in topic 4.2. If the difference in electronegativities is between 0 and 1.8, then you would have a polar covalent bond, and if the difference is greater than 1.8, then the bond will be ionic. All right, so properties of ionic compounds, boom, there's sodium chloride. You can see the large chloride ions attached in an alternating fashion with the smaller sodium ions. Now, ionic compounds tend to be solids at room temperature. In fact, they are all solids at room temperature. The structures are known as a crystalline lattice structure. And their conductivity. Now, when an ionic compound is solid, it is not conductive because all the ions are locked in place. They're not free to move around. But when you melt the salt or dissolve it in water, the ions are free to move, and so the ionic substances will conduct electricity when they're melted or aqueous. All right, now, covalent bonding occurs when valence electrons are shared between atoms, and you can work that out just by looking at the word covalent. Co tends to mean shared, and valent, they're talking about the valence electrons. So in covalent bonding, valence electrons are shared, and that, as you know, generally occurs between two or more nonmetals. Now, the definition of covalent bonding is also electrostatic attraction, only this time it's between a shared pair of electrons. All right, so bond lengths and strengths. So here we have some data for various carbon-carbon bonds. We're looking at the bond energy in kilojoules per mole. That is the energy required to break that bond. It's also the energy released when that bond is formed. We'll talk more about that in Unit 5. But we can see as we go from the carbon-carbon single to double to triple bond, the energy required to break the bond increases, so the bonds become stronger. If we look at the lengths of the bonds as we go from single to double to triple, we see that the lengths of the bond actually get shorter. So the rule of thumb is that the more bonds you have, the stronger they become and the shorter they become. All right, so metallic bonding. There's the structure of a metal. Now, in metallic bonding, we also have electrostatic attraction, only this time it's between a lattice of metallic cations and delocalized electrons. And what we mean by delocalized electrons is electrons that detach from the valence electrons that detach from the metal atoms themselves and become free to move throughout the structure. And the delocalized electrons actually explain why metals are conductive and malleable. So they're conductive because of those free moving electrons, which is often referred to as a sea of electrons. And the malleability is explained by the fact that the cations can move around in relation to one another without actually breaking a bond. So if you smash that metal with a hammer, unlike an ionic compound where you'll actually separate the ions, in the metal, the ions can actually slide around. So when you smash it with a hammer, it would just dent instead of breaking. All right, now alloys are combinations of different metals mixed together, and oftentimes the alloys are stronger and harder than the metals that make them up. The reason this happens is because usually when you mix two atoms together, they'll have different sizes, and the larger atoms kind of act like a scaffold holding the other ones together. So here's a good illustration. It's an illustration anyways that I made with paint. Showing bronze. Now bronze is a mixture of copper and tin. Now without the tin atoms in there, copper is actually a really soft metal because there's a decent amount of space between the atoms and because the atoms are relatively small. But when you take those tin atoms and mix them with the copper atoms, because the tin atoms are larger, they kind of act like a scaffold, keeping the copper ions from moving around. And that is why bronze has such a hardness to it, a good hardness to it, and why it's used for making bells. All right, so determining the structure of molecules. To do that, we use what is known as valence shell electron pair repulsion theory, and this just works on the principle that electrons all repel each other, and geometries for molecules are formed by the electrons, the valence electrons in the bonds and the lone pairs all trying to be as far away from each other as possible. So the optimal geometry will be one in which all the bond angles are as far apart from each other as they can possibly be. All right, so before we can talk about molecular geometry, we have to talk about electron domains. So electron domains are just regions of electron density around a central atom. So an electron domain can be either a bond or a lone pair of electrons, where one bond would count as one electron domain and one lone pair would count as one electron domain. So we're going to look at two kinds of geometry: electron domain geometry and molecular geometry. So the electron domain geometry is just determined by the number of electron domains that you have around the central atom. Now the important thing about the electron domain geometry is that it'll actually determine the bond angles in molecular geometries, which we'll see on the next slide. So if you have two electron domains around the atom, the central atom, then the electron domain geometry will be linear. And you probably remember from Chem 1 that the bond angle for a linear bond angle is 180 degrees. And a great example of that would be carbon dioxide. We see carbon dioxide has two double bonds around the central carbon, so that counts as two electron domains, which gives us that linear shape. If there's three electron domains, we get the trigonal planar shape. And the bond angle in trigonal planar is 120 degrees. And an example of that would be boron trifluoride. Finally, if there are four electron domains, then your electron domain geometry will be tetrahedral, and the bond angle will be 109.5 degrees, and an example would be methane. Now, it's important to note when we see the structure for methane, the way we see it drawn out is looking like the bonds are all 90 degrees and in the same plane, but that really is not the case, and let me show you with this demonstration. So if I make a tetrahedral shape, if I add four bonds here, we see that all of the bonds are equivalent. If I rotate this molecule, program's moving slowly, so that this atom is pointing straight out toward us. If I rotate the molecule this way, we'll see that now that atom is pointing straight out toward us and all the other atoms look the same. So it doesn't matter which way we rotate this molecule, all the bonds are perfectly equivalent. Okay. So next let's talk about molecular geometry. So the molecular geometry is the actual geometry of the molecule. It's the actual shape of the molecule that we see if we were able to zoom in and look at it. Now that is determined by the number of domains around the central atom that are bonds or lone pairs. And changing the number of bonds or lone pairs will determine what the overall shape is. So just here, I just want to note really quickly, if there's two electron domains around the central atom, then both the domain geometry and the molecular geometry will always be linear. But sometimes the same electron domain geometry can give rise to more than one molecular geometry, which we'll see here. So just to give you an idea of this notation here, when we see A, B2E, well, this is just formulas showing A as the central atom, B as the number of bonds, and E as the number of lone pairs. So if there are if there's three electron domains, then we know the electron domain geometry will be planar. Now, if one of those domains is an electron, or is a lone pair of electrons, and two of them are bonds, then the molecular geometry we'll actually get is bent. Now, again, I mentioned before that the bond angles in the molecular geometries come from the electron domain geometries. Now, the electron domain geometry for planar is 120 degrees. But lone pairs, when we replace a bond with that lone pair, we have to take into account that lone pairs actually take up a little bit more space than bonds do. And so the lone pair will actually push those bonds a little bit farther apart from each other, or a little bit farther apart from the lone pair than they would if it was just three bonds. So the bond angle we would expect to see is actually slightly less than 120, and specifically it's 119 degrees. Now, I know it's evil, but you have to know these actual bond angles. And as long as you can remember the electron domain geometry bond angles, then for each bond we replace with a lone pair, you just have to know that the bond angle will be slightly less. Now, for most of the IB questions I've seen concerning this particular geometry with planar electron domain geometry and one lone pair, they will accept anything between 115 and 119, but 119 is the best answer. An example of that would be sulfur dioxide. Now, if we have 4 electron domains, the domain geometry will be tetrahedral. But with one lone pair and 3 bonds, the shape that you get is trigonal pyramidal. Now, the tetrahedral electron domain geometry bond angle is 109.5. So if we replace one of those bonds with a lone pair, we'd expect the bond angle to be slightly less, and so it is about 107 degrees. And an example of that is ammonia. Now, when you see this notation here, this is called wedge and dash notation. You won't see this too often, but in case you do, it's just trying to show a 3D representation where the straight line bond is just in the plane with us, and the wedge bond is a hydrogen that's kind of supposed to be sticking out toward us in space, and the dash is kind of heading behind us. And it does kind of look a little 3D-ish. And finally, if you have 4 electron domains with 2 lone pairs, the domain geometry will be tetrahedral, but the molecular geometry will be bent. Now, we notice here we had the bent geometry from the planar electron domain geometry, which had a bond angle of 119. But because the molecular geometry bond angle comes from the electron domain geometry, then this bent shape will be slightly less than 109.5. And if we add 1 lone pair, it becomes 107. If we add 2 lone pairs, the bonds get squeezed a little bit more, and so the bond angle becomes 104.5 degrees. And a classic example of that is water. Okay, Lewis structures. Now, drawing Lewis structures is actually pretty easy, especially once you get the hang of it. It may seem hard at first, but I recommend just practicing. So here are the steps. The first thing you want to do is count up all the valence electrons in the molecule. Next, arrange the atoms spatially so that the least electronegative atom is in the center. Now, we can determine the least electronegative atom by using what we know about trends in the periodic table, or by looking in the data booklet in, I can't remember what table it is, I think it's table 8 or 9. All right, and then start by connecting the atoms to the central atom with single bonds, and distribute the rest of the electrons as lone pairs to satisfy the octet rules, starting with the outside atoms first. Next, we check that each non-hydrogen atom has access to 8 electrons, and that each hydrogen has access to 2. It's important to note that boron is an exception, which is satisfied with 6 valence electrons, as in boron trifluoride. If you're satisfied, then move on to step number 5. If not, we have to add multiple double and triple bonds to satisfy this rule. So pairs of electrons will be shared in order to make everybody have their stable octet. And finally, double check that the total number of electrons in your structure is equal to the total number of valence electrons that you added up in step 1. All right, so let's look at a couple of examples. So for ammonia, first thing we're going to do, add up the total number of valence electrons. There's 5 in nitrogen and 3 in hydrogen for a grand total of 8. We'll then arrange the atoms so that the most electronegative is in the center. Now with hydrogen, we know that hydrogen cannot be a central atom because it can only make one bond. Right? So then we can connect the atoms with single bonds and then distribute the remaining lone pairs. So each single bond consists of 2 electrons, one from nitrogen and one from hydrogen. So we've already put 6 electrons around here. So we have to put 2 more, in this case around nitrogen, because we can't put any more electrons on hydrogen. Sorry, it's late at night. So for this molecule, we see there's 4 electron domains. So the domain geometry will be tetrahedral. But because one of them is a lone pair, the molecular geometry is trigonal pyramidal, and the bond angle, slightly less than 109.5, is 107 degrees. Now for carbon dioxide, add up the valence electrons, 4 in carbon, 6 in oxygen, and there's 2 oxygens for a grand total of 16. Arrange the atoms so that the least electronegative is in the center, that is carbon. Connect with single bonds. We've distributed 4 electrons, so we have to distribute 12 more. All to the oxygen atoms first. So here they come. Boom, 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 boom. Oop, oop, oop. Too far. All right, so there we have our 16 electrons. Now we have to check to see that all the atoms are happy. Now we know that oxygen likes to make 2 bonds generally, and carbon likes to make 4. So each oxygen only has 1 bond coming from it, and carbon has only 2. So what we're going to do in this case, each oxygen atom is going to share a pair of electrons to make a double bond around carbon. So we know the structure of carbon dioxide looks like so, and that is what we get. Now here, there's 2 electron domains, so both the domain and molecular geometry will be linear, and the bonding will be 180 degrees. Now again, look at compounds, practice drawing Lewis structures. This is a pretty foolproof method as long as you follow the steps each time. All right, so coordinate covalent bonding is covalent bonding where one atom donates both of the electrons in a bond. A typical covalent bond is 1 electron from one atom and another electron from another atom shared. They each donate 1, but in a coordinate bond, 1 atom will donate both of the electrons. A classic example of that is carbon monoxide. We look at the valence shell of carbon and oxygen. We know that carbon has 4 valence electrons and oxygen has 6. So oxygen really only has 2 electrons available for bonding and carbon has 4. Since there are 6 electrons shared between them in a triple bond, 2 of the electrons must come from carbon. So one of those 3 bonds in the triple bond is the coordinate bond. Another example is the ammonium ion, which is formed from ammonia and a hydrogen ion. So ammonia is NH3 with a lone pair of electrons on nitrogen, and a hydrogen ion is just a hydrogen atom that lost its lone electron, so it's essentially just a proton. And the hydrogen ion will just attach to the ammonia, not supplying any electrons to the bond, so our coordinate bond is right there. All right, resonance and electron delocalization. So electrons in double and triple bonds are actually free to move between adjacent equivalent bonds. And that has a really important effect of equalizing the bond lengths and strengths between equivalent bonds. Now, if we draw resonance structures, the first thing I want to look at is the nitrate ion. So when we draw the nitrate ion, we see that nitrogen is covalently bonded to 3 oxygen atoms, with one of those bonds being a double bond. Now it's important to note when we draw the structures for polyatomic ions that we put the whole ion in brackets with the charge of the ion outside to show that the charge is distributed amongst the whole thing. Now, there's 3 resonance structures for the nitrate ion. We can see them here, one with a double bond pointing straight up, one with it off to the left, and one with it off to the right. Right. Now, what is actually happening in this nitrate ion is the electrons in that double bond are actually free to move wherever they want around the molecule. So what we would expect to see is the nitrogen-oxygen double bond being stronger and shorter than the nitrogen-oxygen single bonds. But what we actually see when we look at the data is all the bond lengths and strengths in the nitrate ion are all the same. So take a minute, pause the video, draw the Lewis structure for the carbonate ion. Now when you do that, remember to add 2 additional electrons for that -2 charge, and try to draw the 3 resonance structures we get for that. Alright, so just like the nitrate ion, the carbonate ion has 1 carbon-oxygen double bond and 2 carbon-oxygen single bonds, so there's 3 resonance structures, and there you have it. Okay, so what we need to know is physical evidence for the structure of benzene. All right, so we know that benzene looks like this. It's a hexagonal ring with one hydrogen coming off from each carbon and alternating double and single bonds. You can also see it written most often as the skeletal structure of benzene, or sometimes just a hexagon with a circle in the middle. Now the key to this evidence is resonance, because what we actually see in benzene is that all the carbon-to-carbon bond lengths and strengths are equivalent. If this were a straight chain triene, what we would expect to see, first of all, it wouldn't have the molecular formula C6H6, but we would also expect to see stronger carbon-carbon double bonds and shorter carbon-carbon double bonds. But since we don't see that in benzene, we know that this must be the structure. Okay, finally, allotropes of carbon. So an allotrope is just different physical form of the same element. And the classic example we use in this class is carbon, which has several different allotropes. And that's why I say, isn't carbon awesome? It does so much stuff, and diamonds are forever. Okay, so there's 4 allotropes we have to know about. You have to be able to describe them in terms of their structure, their strength, and their conductivity. Also, in the bonding, as in the number of the number of atoms each carbon is bonded to. So in a diamond, what you have is covalent network bonding, and each carbon atom will be bonded to 4 other carbon atoms. Now, network bonding refers to something that is not molecular or not made of molecules. If you look at the structure of diamond, each carbon is bonded to 4 other carbon atoms. And the whole structure is basically like one big, huge molecule. The next one is graphite. Now, graphite is also network bonding. And what you have is layers of hexagonal rings with each atom bonded to 3 other carbons. In the illustration here and in the words here themselves, the bonding within each layer of graphite is very, very strong. But there's very, very weak intermolecular forces between the layers. That is why it's really easy to peel away layers of graphite, like when you write with your pencil. It's easy to leave graphite on the page because of those weak intermolecular forces. Now, graphite has very, very strong conductivity because there are delocalized electrons free to move around. Now, in diamond, there is no conductivity because all the electrons are tied up in those single carbon-carbon bonds. The next one is graphene. Graphene is just a single layer of graphite. So there's also covalent network bonding. Each atom is bonded to 3 other carbons. You can actually roll graphene up into what are called carbon nanotubes, which are really, really going to be the wave of the future with electronics and computing. They're really, really strong and flexible, and just like graphite, they're very, very conductive. And finally, the C60 Buckminster fullerene, which is as fun to say as it is to say. And again, it's 9 o'clock on a Friday night, so I'm a little goofy. So the C60 is the only one of these 3 allotropes that has a molecular structure. In other words, it's instead of being one big, huge structure, it's actually made out of molecules. And what you get in there is 20 hexagons and 12 pentagons, so it looks just like a soccer ball, and each carbon is bonded to 3 others. Now, there's strong bonds within each molecule, but the forces between them are weak. And finally, they're not conductive, because electrons cannot jump from one C60 molecule to another. And that is topic 4.1. If you have any questions, please bring them to the class, and thanks for watching.